All right, and 6.1c is the last section of 6.1, and it's just called Euler's method. I know you think this is pronounced Euler. It's actually pronounced Euler. He's Swiss. That's how they say it in that. Euler's method. All right, so Euler's method, and if you call it Euler's method, you're not wrong. Euler's method, approximating the solution at a point. So this is not on the AB. So this is the first thing that some of you are doing that is BC only. So those of you that were in AB last year, congratulations. This is finally new. So use Euler's method to approximate the particular solution f of 2 of the differential equation y prime equals x minus y passing through the point 0, 1. Use 4 steps. So we want to get from the point 0, 1, so like we've got, say, this graph, and say 0, 1 would be like right there, and we want to get over to f of 2. And we don't know where it is. Maybe it's down here, maybe it's up here, maybe it's up there, who knows. But the way we're going to get there is we're going to break this up into 4 steps. So like 1, 2, 3, 4. Each of those is our delta x or dx. And we're going to figure out what the slope is at each point, and we're just going to go by the slope. So like let's go ahead and start. So we'll start at 0, 1, and we're going from 0 to 2. So like our a is 0, our b is 2, so our delta x is 2 minus 0 over the 4 steps is 1/2. I'm just going to use 0.5. So now we're going to figure out, okay, how much up are we going to go? Well, we know y prime, which is this part right here, is just x minus y. So we're going to see how much, what's our change in y going to be? So our change in y is going to be equal to x minus y. Well, here's x and here's y. So it'll be 0 minus 1 times dx, which is times 1/2. So we get -1 times 1/2, so we get -1/2. So what actually is going to happen for the dy is it's going to go down by 1/2 to get to this next point. All right, so that means our x now is going to change by 0.5. It's positive. So our x after our first step is going to be 0.5. Our y, if we go down by 1/2, we're going to now be at also 0.5. Our dx is still going to be 0.5. In fact, it's going to be 0.5 for the whole time. We're not going to take a step here because this is where we're going to end as our 4th step. All right, so now our dy here will be x minus y is 0.5 minus 0.5 times 0.5, our dx. So that's 0. So that means our y isn't going to change any. So that means we're going to stay flat here for this next section. So our x is going to go up by 0.5, which will be 1. Our y will be 0.5 plus 0, which is going to say 0.5. So now our change in y will be what the slope is there. So that's 1 minus 0.5 times 0.5. 1 minus 0.5 is 1/2. 1/2 times 1/2 is 1/4, so 0.25. So now we're going to go up a little bit by 1/4. So our x is going to change to 1.5, always going up by 0.5 each time. Always going up by our whatever our delta x is. See, 0.5, 0.5, 0.5. So now we've taken 1, 2, 3 steps. Our y, we're going to go up by 0.25. So we add in this to this. We get 0.75. So then our new change in y will be 1.5 minus 0.75 times 0.5. All right, so 1.5 minus 0.75 is another 0.75. So this is 3/4 times 1/2 is 3/8, which is is that 375? Is that what that works out to, I think? Someone will tell me if I got it right or wrong. I think that's it. All right, so that means we're going to be going up by 0.375 to get to the next point. So we're going to go up some more, and that's going to be where our point is. All right, so our x, if we go up by another 1/2, will get us to 2. That's what we wanted to do. We wanted to find what's f of 2, so we're at the end point for f. All right, so we go up by 0.375 here, so this is 0.75 minus 0.375 is going to give us 1.125. So that means f of 2 should approximately be 1.125. All right, and that's how we do Euler's method. All right, so now we've kind of done this before, but we didn't keep changing the step. We found the equation of a tangent line and we just used that to approximate. That's like doing it all with just one step. All right? Usually we do it with 2 or 3 steps because it gets a little more accurate with each step because we're getting the new slope at each point. We're basically following that slope field to get to that next point. All right, so let's try one more here, and then that will be the end for Euler's method. So given that y of 1 equals -3, and the derivative is 2x plus y, what is the approximation for y of 2 if Euler's method is used with a step size of 0.5 starting at x equals 1? All right, so remember, for Euler's method, we had x, we had y, we had delta x, and we had our dy, which was f primes, or the derivative here, which is 2x plus y times the delta x, or times the dx. So make the chart. Right, this is what they want to see on the AP exam, especially if it's on the free response. Just make the chart, and we are starting at 1, -3. So 1, -3. Our delta x is 0.5, again. So that means our dy will be 2 times x, so 2 times 1 is 2, plus -3, so -3, times 0.5, which gives us, let's see, that's -1 times 0.5, so -0.5. So now our x is changing by the delta x, so that'll be 1.5. Our y is changing by this, so that means it's going down by another half, -3.5. Our delta x is still a half, that never changes. Our dy is going to be 1.5, 2 times that, so it's going to be 3. All right, forgot the 2. Did the 2 last time. So 2 times 1.5 is 3, plus y, so minus 3.5, times dx. That's usually what people forget, is the dx, or the delta x, if they do this wrong. So we get -0.5 times 1/2 is -1/4. So we go another 1/2, and we're to 2. Well, that's where we want to be. We wanted to stop at 2. So we're going to stop here. We don't have to keep going. All right, so now we just need to go from here down another quarter. So it's going to be -3.75. So that's what our value is. So we say that y of 2, our function was called y here, is approximately equal to -3.75. There it is. All right, so that's how Euler's method works. Make the chart and just trying to fill in the chart, guys. It's not hard. It's just the same thing over and over and over again. All right, so that's Euler's method, and this is the end of 6.1. So check out the homework on Google Classroom.